phosphate is pH neutral, and it's the phosphate that will change the pH. It is a weak base anion because it's not hydroxide, so it's not strong, and it's not one of the 8 anions that are pH neutral. All other anions are not going to be pH neutral. So phosphate is a weak base. So you're going to write its weak base dissociation. So again, I recommend that you write down that it's a base and then remind yourself what that means. Everything is just moving a hydrogen. And so it's a base. So the base will accept a hydrogen. So it becomes HPO4 -2 aqueous. And a base forms hydroxide in water. The hydroxide comes from the water molecule that lost its hydrogen to phosphate. So that is the weak base dissociation. Then you want to write its expression, and the expression, because it's a base, will be a Kb expression. So it'll be Kb, and then the products. So the conjugate acid times hydroxide over the weak base anion that dissolved. So that is the Kb expression. So the expression is always going to be the constant is equal to the products over the reactants. So then it's on to organizing the equilibrium data, which means you have to have a constant that you either look up or calculate off to the side, and you set up the chart. So the chart, just do it first. The concentration of the ion, it's a 1-phosphate in this compound. And so the concentration of that ion is just the 1.5 molar. And there's 0 of the product to begin with, and X amount dissociates to form X and X. So at equilibrium, you have 1.5 minus X of phosphate and X there. So this part of the expression will just be X times X over 1.5 minus X. The constant is not going to be in the Kb chart. So we have to look up the conjugate acids Ka. So this is the conjugate acid, HPO4 -2. So under phosphoric acid in the Ka chart, you will see phosphoric acid, and then the hydrogen phosphate ion, or the dihydrogen phosphate ion, and the hydrogen phosphate ion, HPO4 -2. And so this Ka is 4.2 times 10 to the -13. So I'm gonna write this on the back here, the off to the side calculation. So the only way to get the Kb that we want is to look up the Ka. Okay, so we have a base, and that's going to be for phosphate. And we have to look up the Ka of the HPO4 -2. So it's very important that you label the base and then the conjugate acid, or the acid and the conjugate base, so you get the right formula that you're looking up. So I need this Ka for this substance. So this is in Appendix H. So again, it's 4.2 times 10 to the -13, and that equals our times our Kb equals 1 times 10 to the -14. So our Kb is going to be water's constant divided by hydrogen phosphate's constant. Okay, so I have a -14 divided by a -13. Our answer is our constant is going to be much bigger than the other constants that we have previously seen. Still weak, because it's going to be less than 1, but it is a stronger weak one. So 1 exponent negative 14 divided by 4.2 exponent negative 13 equals 2.4 times 10 to the negative 2. This is not the equilibrium expression. This is just the constant. The expression, this is one side of the expression. The other side is the x times x over the initial concentration minus x. So this is the constant that we have to use. So these are all the parts. You have to write out the correct acid-base dissociation and then write the expression. If it's an acid, you will do Ka expression. If it's a base, it's a Kb. And then either you look up the constant in the acid or base chart, or you have to look up its conjugate's constant in the acid or base chart. You will set this up and plug it in, and it will always look like x times x over initial concentration minus x if it's weak. If it's strong, there is no equilibrium expression. Okay, so now we do the math. Okay. Why did you get a sad face about to do the math? We cannot always do the shortcut because sometimes x is big, and if x is big, when you subtract x from your concentration, it's going to affect it, which means that x is going to be big enough that I can't ignore the quadratic equation. So you can only ignore it if that times 10 is to the negative 4 or smaller, and negative 2 is bigger than negative 4. So we cannot ignore it, but it's not like a big polynomial or anything where we have a whole polynomial on top and bottom. We're going to have x squared on one side, and we're going to distribute this over here. And so we've got 2.4 times 10 to the negative 2 times 1.5 minus x equals x squared. Okay, so 1.5 times 1.5 times 0.024. I'm going to write it as a decimal number because it's big enough. Minus 0.024x equals x squared. So I just rewrote the scientific notation as a number. Okay, I'm going to move everything over to the x squared side because that's the bigger x squared side, and I do not want a negative x squared. Because if I bring it over here, it's going to be minus x squared, and my a will be negative, and then you got to factor out a negative, which I guess you can do if you want to. But I'm just going to move these two values to this side. And so I'm going to subtract my number and add my x value to the other side. So I will get 0 equals x squared plus 0.024x minus 0.036. So my A is 1, my B is 0.024, and my C is negative 0.036. So it's not as crazy as the stuff we previously did, because our A is going to be 1 every time because it's going to be x squared. It's always going to be x times x. Okay. So x is equal to negative b plus or minus the square root of B squared minus 4AC over 2A. I got that for my X. I didn't do the minus because it'd be minus and minus, and X is a measurement and can't be negative. Anybody else get this? I'm doing this in real time, so I don't like have the answer. Okay, this is X. So the reason we could not ignore it is because if you subtract this from 1.50, it is going to affect it even when you round. If you round to 3 significant figures, it's going to be 1.3 something. So it's going to affect your initial concentration. It's big enough. But this is the molarity of hydroxide. So X is going to be for bases, X is going to be hydroxide, and for acids, it's going to be hydronium. Because this X amount forms. So this would be the molarity of the hydroxide.